Hello everybody, this is a video to show you about setting up your OpenCV and CUDA together as one single project, and then how you can open up an image and process its pixels both serially and in CUDA, and this should be helpful with helping you write your project. And I will go through the steps that you need to take. Please bear in mind that some steps may be different when you're working on your project number one, but this video should be helpful in showing you how to set the projects up, how you can read an image and associate data values to it and work with the data values that are associated in this image. So first things first, what we're going to do is we are using two projects, and we're working on two projects, two libraries. We want to work with our CUDA library and with our OpenCV library. And so, as you remember, when you're setting up a library to work with your project, you will have to make sure that the header files and the include directories are associated so that you could use those header files in your project. Also, your library files or .lib files are accessible to your linker so that your Visual Studio compiler can compile and link your program. And to execute the binary files, the executable files of your library, you would have to show where the dynamically linked library or the DLL binaries are. When you're doing this for two projects, we will have to do these steps for every single one of the libraries that we are using. So what we're going to do here is we're going to build our project off of a CUDA template so that all of the data associations and the libraries from CUDA are accessible, and then we will be adding our OpenCV to this code. So again, I'm going to go and create a new project, and I'll make my project a CUDA 5.5 runtime. And I'm going to put this project in my OpenCV CUDA projects folder. And then this project that I will show you takes an input image and converts its values, a grayscale image, and converts its values from it basically negates the image. So if you remember or know about old style photography, the pictures that you would take with analog cameras on film, they would be developed as negatives, and then you would convert that negative into a positive image. So we're going to do an image negation project. So let's call this image negation CUDA. Right. As you see here, when the project is set up, it will basically have a kernel.cu file. Now, for your project, I created a kernel shell. So all you need to do is to go and copy and paste the stuff that comes from my kernel and paste them into your kernel. So when you do that, your project is going to basically look like an empty project, and I'll call this function, instead of add kernel, I'm going to call it GPU kernel, and then I'll just delete the data that comes with this function. So I'm just going here, and I'm going to just go ahead and delete all the unnecessary materials that I have with my template to make this function an empty function that compiles. Okay, and then we'll call this GPU kernel. And then I'm going to call this a grid and a block. And then I'm going to here later on define the grid variables, grid variable and the block variable. Basically, grid is the size of my grids, how many blocks I have in my program, and block is the size of the block, which is how many threads there are in the grid. And this is basically my empty code, with the exception of these CUDA mallocs that I have and the CUDA memcopies that I have for my project. So now that I have this project set up, I'm going to go ahead. Actually, let me just delete these CUDA memcopy and CUDA mallocs, because right now with having these materials, my program is not going to compile. So I just want to make sure that my program compiles as a completely empty shell. Okay, let's compile it. And it should have succeeded, which it did, because there's no error in the code, as you see here. Since I have everything are just basically empty stubs. In the main, I basically call my my CUDA function, and let's call this negate with CUDA. Then we're going to change the name add with CUDA to negate with CUDA, and change the name of this function negate with CUDA. And then if we succeed, we print CUDA succeeded. Let's call this CUDA succeeded, and then we reset the device. If there's an error, we show that there's an error. Then in the negate with CUDA, as of now, I'm just declaring 3 device pointers. Set the device, and then invoke the kernel, get the errors, synchronize the device, and if any error occurred, we just release the pointers. And if no error occurred, we just jump and we return to the CUDA status from that point on. Okay, let's see if my build succeeded here. Yes, the build succeeded. Alright, next we're going to add our OpenCV materials to this project. Notice to add your OpenCV materials, you need to add the header files into the additional include libraries folder. Since I don't have a C++ file in this project, when I right click and bring the properties of my window in, you see that there's no C++ folder here. I need to have that folder in, so I'm just going to go and just add a dummy CPP file or an empty CPP file, and let's call it dummy file. And there, with my project, it's going to be empty. I'm not going to add anything to it. When you click on your project properties, now you see the C++ open up. So you need to add your additional include libraries there. So how are you going to do that? You're basically going to bring in either the environment variable that you set for your OpenCV file, or just type in the path to your OpenCV header files. My environment variable is OpenCV underscore dir, and then from there I'm going to go into the include file. And then when you apply, the way for you to realize and notice whether that was the correct library is when you go in here in your code and you attempt to include OpenCV libraries. When you open up, you should be able to see the OpenCV folder. And from there, you should go and add the cv.h and include OpenCV /hi GUI.h. These two files are the header files for image processing application that we are writing. So we could use the functions such as mread, mshow, and also functions such as or variable or objects such as mat, images, and so forth. To be able to use those, we need to add the cv.h and the high-gui.h as you see here. And these files are in the OpenCV folder. So what I did is I right-clicked and went to the properties of my project. After I added a C++ file, I went to the C++ and then clicked on the additional include libraries and added my library. Notice this OpenCV_dir is an environment variable that I created so that my path OpenCV from C:\gaming /OpenCV /build, whatever folder that is included there in this project. So now that I have that, I'm going to have to go and add my additional linked libraries also. These are the libraries that point to my linkages. So to do that, I basically do the same thing. I set up an OpenCV_dir_32_VC10 environment variable that points to my Visual Studio 2010 32-bit compiled binaries, or rather libraries, of OpenCV, and they're all in the lib folder. You can either do that, or if you don't have this environment variable, you basically have to add the whole path. To do that, you click on Open, and then Edit. And then when the window opens up, you see it's already added here. You can click on New Folder, and then from there you type in C:\\. It opens up all your folders, and then my OpenCV is in the gaming programs. And then when you backslash, you see that the folders are added. So mine is OpenCV, and then /build /. Then you need to point into the x86 /VC10 /lib. That is where my library files are created or installed when I installed my OpenCV software. So your folder may be different. So that's how you add your libraries, and then to be able to execute this program, you would have to basically add the path to the binary files also. So since my binary files are in OpenCV folder for /bin, just kind of side by side to where the .lib files are, I'm just going to go to the debugging tab and add my OpenCV binaries directory to the debugging working directory. There's one last step that's left, and that's another linker step to add the libraries that I'm going to physically use. Those libraries are OpenCV core and OpenCV high-GUI. To be able to do that, you basically go and click on additional dependencies, click on the little triangle arrow, open it up, and then you go and add into this folder your OpenCV_core, then the version of your OpenCV, mine is 247 d.lib, and then OpenCV_high-GUI, the version d.lib. Again, OpenCV is the name of the project, the name of OpenCV library, an underscore, then the name of the library itself. I'm using two libraries, core and high-GUI. then the version of the libraries. Mine is 247, yours may be 248 or 230, whichever version you installed. And then D stands for debug, because I'm actually in the debug mode, because my active mode configuration is debug. And then press open, and that adds these OpenCV libraries. How would you know what your libraries are and which versions you're using? It's very easy. Open up my computer window, go to wherever the OpenCV is installed. In my case, it's in Gaming Programs, OpenCVs, Build, and then the x86 and VC10, and then Libraries, and then you see your libraries there. So mine are OpenCV underscore core 247D. See, OpenCV underscore core 247D, and then OpenCV high GUI 247D, OpenCV underscore high GUI 247D.lib. So with this, I should be good. Next, I'm going to open an image and show its content in my main folder. It's a fairly straightforward process, and for the sake of this application, let's just comment out the CUDA error, CUDA status equal negated with CUDA, so that I will not have to okay, so let's let me actually create the CUDA status variable and then comment it out. Okay, so I'm going to just bring this to the beginning of my program so that it would work. Okay, so I just commented out the function that performs my operations on CUDA, because at this point I don't want to, it's empty, it's not supposed to do anything. And then the first task that I wanted to do is to open up an image and show it. So in OpenCV, the images are of the form of mat. But see, I don't have a mat variable defined, because there's a namespace for the mat, which represent matrices. So in order for me to be able to use this, I'm going to actually use this namespace into my project. So let's go right where my preprocessor's directives are and perform a using namespace CV. And while I'm at it, I'm also going to, well, let's leave it at there. And then I'm going to basically then create a matrix for an image. So it's going to be mat, and then I'm going to call it input image, and I'm using imrid, and then imrid takes two variables, the first or two arguments. The first argument is going to be the location of the image, the full path, and the name. And then the second argument is a flag if you wanted to read it in a specific format. So my images are in C images, and then I'm going to read the lighthouse image. And I'm going to read a grayscale image, lighthouse underscore gray. These files should be also included in your project description on Blackboard. So I basically downloaded them, and so lighthouse underscore gray .jpg is where the file that I'm loading. Then I'm going to basically test to see if the image loaded. So I call it input if input image dot data is not loaded. I'm going to printf image didn't load properly. And if my image loaded properly, then I'll perform my tasks. Let's compile and see if this worked. Okay, my build succeeded, and as you see here, build 1 succeeds 0 failure. And then if I execute this program, I get the image didn't load properly message. Let's see what problem there was. I may have misspelled the name of my lighthouse. Yes, Gray, and I misspelled it Gary. Okay, lighthouse Gray. Another error in the name, lighthouse. Okay, now this worked, and as you see, I'm not showing that error message, so my program is working. The problem is that I don't see really anything happening to it. It's because I really don't have anything else written in this program. It's basically an empty program. It opens an image and then it just closes up everything because it finishes. So now let's show this image. I'm going to use imshow function. The imshow function takes an image that you just read in an IPL image pointer, which is the image processing object for an image, or a matrix, and then it just shows that on a window. The two arguments that go is the name of the window. Let's call this input underscore image, and then the data, the matrix that you want to show, and in my case it's called input image. Okay, if I run this program, something peculiarly curious happens, and that is it opens up the image and it immediately closes it. And I didn't even notice anything happening because my computer is so fast I didn't even see the window open and then pop close. So to be able to see the materials that I'm creating and the images that I'm showing and everything, I use a pause command. In OpenCV it's called cv_wait_key, and cv_wait_key takes an argument which is the time that you want it to pause before moving on. In my case, I want it to pause until I press a key. So I'm going to basically use cv_wait_key 0. The number that you give it as an argument is the number of milliseconds that you want this program to pause. So 0 is basically 0 milliseconds, which pauses for user input. If I do cv_wait_key 1000, it waits for 1 second. If I do cv_wait_key 5000, it waits for 5 seconds. And as you see, my project ran, and this is the image it shows, which is the lighthouse. So I opened my image of lighthouse, I put it in the input image matrix, and then I used that matrix to show on the window called input image, and that shows my image. So imshow shows, imread reads the image, and then when I press any key, it exits out my program. So next step, what I would like to do is to create a variable, another matrix, and I use this matrix and I call it CPU negated image. And so to be able to set this, I'm going to use mat as a matrix, and then let's call it CPU negated image, and then I'm going to create this image the same size as my input image. So I want the number of rows to be input image dot rows, the number of columns to be input image dot calls. And then what I would like to do is for this image to hold a grayscale data, which is an 8-byte value for each pixel. That is basically CV8 unsigned character 1 data type. So CV8 unsigned character 1 is a data type that's basically 1 byte long, because I'm using grayscale images. Grayscale images are 1 byte long, and this long, and CV8 UC unsigned char 1 means that each pixel is 8 bytes, it's unsigned, of type char, and it contains 1 byte per pixel. So this creates my image. Let's just show with an ImShow how this, let's call it CPU output, should look like. And the image is going to be CPU negated image. Okay, if I ImShow this, it's going to probably show a grayscale, a completely gray image. Oh, I mistyped ImShow. So ImShow CPU negated image. Alright, that was my original image, and this is my CPU negated image, CPU output. And as you see, it's basically, since I created it the same size as my original image, the sizes are the same, but this contains just junk values, which is basically a gray value. So what I would like to do is I would like to create a function. For this function to take as input 2 arguments, the input image and the output image, and then to negate these on the CPU. So let's create a prototype for this function. CPU code. That's what I will call this code. And then this function is going to be basically, let's make this a void function, and let's call it CPU, or CPU negate. And to pass into this function, I'm going to pass a reference to my output image so that I could reserve memory and I could access the original values from my main function that are on the destination image or output. And then I'm going to pass another reference, and that reference is going to be my my input image. So I'm going to pass a mat reference as destination and a constant mat reference as the input. So this is the prototype of my function. Then how am I going to do the negation here is inside of the else, if I actually did indeed open an image and it did work, then I'm going to go and call the function CPU negate that I just created up there, the prototype for it. I'm going to pass to it my output, my CPU negated image, and then my input image as values, as references. So see, what happens here is on line 37, I'm going to call CPU negate, pass to it my CPU negated image, which is the grayscale image that I just created, and the input image, which is the image that I read. And I'm passing these on line 22, I'm passing them by reference. There are good reasons to do this. If you pass by value, you're basically creating a local variable of that object. There are two things wrong with it. One, your memory requirements are going to be doubled because a matrix data type is a huge data type. When you pass it by value, you have to create a local copy of it, which is not really a good idea to do in terms of memory. Also, when you pass by reference, you get access to the original data, so you could work with the original data here and keep the changes. Great. Now let's go and implement this function. To implement this function, I'm going to call this function just as I did, CPU implementation, and then this function was a void, and I call it negate CPU negate. CPU negate, and then I pass a mat reference. Let's call it destination, and then a constant mat reference. Call it source. So we're reading from the source image, and then we're writing into the destination image. The logic here is simple. I'm negating the image data. So to do this, go over each pixel, and then for each pixel, all I need to do is to basically calculate output to be 255 minus input on that pixel. So the first thing is to define where my pixels are. If you have an image with the size row and column, with so many rows and so many columns, each pixel ij is going to be at a certain location. So I'm going to create an int, call it row equals, or rather rows equals source dot rows, and this variable gives you how many rows there are in your column. And then we'll do int cols equal source dot columns. This gives you how many columns there are in your image. So then I'll need to write a for loop. For int I equal 0, I less than rows, I plus plus, and then inside we'll do a for loop, int j equals 0, j less than columns, j plus plus, and then we'll have to create, let me just put all these braces, and then from this point, for each of the images at location I, location j, I'd have to calculate the actual index of the image. And the index of my image is going to be j plus I times how many columns there are. So create an index variable, and this is going to be j plus I times columns. So this equation takes a location ij and calculates its actual location in the data pointer value of your image. And all you need to do is to create your destination at location index to be equal to 255 minus source at location index. Oh, it's destination.data and then source.data. So we'll take the data value at location ij of the source and then calculate 255 minus its value and put it into the destination. This project is the CPU side code that takes two images, a source image and a destination image, and for each pixel it calculates the negative. Let's run this, see if it works on the CPU side. Okay, I probably miscalculated something. Okay, here's the output of my program, and I'm glad I ran it because this is an error. The output image should be exactly the negative of the input image, but it's not. And the reason for that error is that when I read my original image, although it was a grayscale image, I read it with the default parameters, and the default imread reads an image, even if it's a black and white image or a grayscale image, it reads it into a three-dimensional or an RGB colored image. So to read a grayscale, just read your image as imread of the name of the image, comma 0. This reads your image as a grayscale image. And when you run this program, after you correct this error, you'll basically get the result, which is a negation of your original image. So if this is my original image, as you see, my negated image is going to be basically just complete negative of it. So that's on the CPU side. And so on the CPU side, as you noted here, I'm passing the CPU negate image and the input image, and that negates my image, and it basically steps through every row, every column, calculate the index, and then perform the operation. So easily you see, if I port this into GPU, I'm going to get these two loops taken care of. So I'm going to make the loop invariance, take out these two loops, and port my code into CUDA. The good news is that I have the stub of my code. See, I've already created a negate with CUDA. So what I'm going to do is I'm going to pass this to this negate with CUDA, just the same thing I did. A matrix reference and a constant matrix reference. So with my negate with CUDA code, also here I'm going to create a, let's create a GPU matrix for a GPU image. So let's call this GPU negated image, make it the same size as my input image dot rows input image dot calls cv underscore 8-bit uc 1 byte long character, unsigned char 1 byte long character. And then in my negate with CUDA, I'm going to pass the GPU negated, and let's just go and uncomment. So we have negate with CUDA, we pass the GPU negated image and the input image to it, and we return a status, whether it worked or not. And here, let's call this comment negate with CUDA in parallel. Alright, so that is very good. So next is to go and write our implementation. I kept the function from my template CUDA when I created this project because it has neat little error checking mechanisms to it, and all I need to do is to do the 4 tasks: declare my device parameters, which I already have, allocate memory on device, invoke the kernel, memcopy from host to device, invoke the kernel, and then memcopy back to the host, and I'll be done. So let's do it. It should be fairly straightforward. So I'm going to need 2 device pointers, one for the input image data and one for the output image data. So let's call this int pointer, and actually these will be u or unsigned char, and call it device source, and then unsigned char pointers, and then we call it device dest. Okay, so the source will have my input image data into it, and the destination will have my output created negated data into it. So next, I'm going to go and use CUDA set device to set my graphics card. Since I have one graphics card, I just set device 0. If there's an error, I'll show the error. If not, I move on. And then now I need to allocate my memory on GPU. How am I going to do that? It's fairly straightforward. CUDA memcopy will allocate the memory I need. So to do this, I need to allocate 2 memories on the GPU. So one for input and one for output. So I do CUDA status equals CUDA malloc. CUDA malloc contains one pointer as the GPU side, and then the size that you want to allocate. So, and to void pointer to pointer reference device underscore source. That's my pointer for the source image, and then the size will be size of unsigned char. And how many do I need? If my image has columns and rows, I need the number equal to columns of the image times rows of the image. So see, I passed my mat reference destination image and a constant mat reference source image. Source image is the input image that goes to this function, and destination image is the destination image that goes out of this function. So I need to have source image dot rows times source image dot columns, and that's how many bytes I need to allocate for the device source pointer. Do the same thing for the device destination. CUDA status is the variable that will contain whether an error occurred or not, and then we do CUDA malloc and then void pointer reference of device underscore source. The size of it should be size of an unsigned char times now this is going to be destination image dot rows times destination image dot columns, and that's how many bytes I would allocate for my destination pointer. Or device destination, DST, device destination. So CUDA malloc on the device destination pointer, how many? It's going to be size of the rows times size of the columns times of the destination image times the size of the data pointer itself, which is a byte. And I don't need these pieces of code because I only have 2 memory allocations to do here. The next step is to copy the content of your data from the input image into the source on the device. So we use CUDA memcopy for this case. So we do CUDA status equals CUDA memcopy, and then the CUDA memcopy takes the device side, which is going to be source, the image data that we want to pass to it, which is going to be the input image, we call it source image dot data, and then how many bytes do I want to copy? I want to copy the exact size of the image data in the source image, which is going to be the same numbers that I created up here. So I'm just going to basically use the size of unsigned char multiplied by the rows and the columns of my image, and then I need to specify where do I want to copy these from, and then where do I want to copy these to. So it's going to be CUDA memcopy host to device. So this line of code will take the image data of the source image, my input image, and then copy them into the device underscore source, which is the unsigned char pointer that I created and allocated on GPU. Since I only have one location here, I basically declare it and calculate it. Now, next is to set my program up for invoking the kernel. But before I go there, let's suppose that the kernel will work, and now we want to basically copy the results back to the device. So to perform that, we're going to scroll down into the end of this program, and then here where I says copy output vector from GPU buffer to host memory, I'll do the opposite of what I did with the source image. I copy from the destination image or from the GPU back into my CPU. So I use another CUDA status, and then here I'm going to do a CUDA mem copy, and this time I'm going to write into the device pointer, which is called dest image. The host pointer is called dest image.data, and I read from the device underscore destination pointer. How much I'm reading? I'm reading the size of unsigned char times dest image dot rows times dest image dot calls, and this time I'm going to copy backwards, so it's going to be CUDA mem copy device to host. Okay, so now we copied, and then and also we need to change these guys when we free our devices, free the source and CUDA destination, or device source and device destination buffers. Alright, now the final piece of the equation here is to establish the number of grids, the number of blocks, and launch your kernel. Now when you launch your kernel, we're going to pass to this kernel the pointers that we're going to be working on. And the 2 pointers that I'm going to be working on are going to be a pointer to the device and a pointer to the destination. So I'm going to pass device underscore dest and device underscore source. So the first one is the destination pointer, the second one is the source pointer from the global memory that I will use. I need to go into here and make my kernel also prototyped well. So I'm going to use an unsigned char pointer dst and a constant unsigned char pointer src. So that's the prototype of my function. I pass the data pointers to them, and as you see here, I'm passing the data pointers properly. The first one is the destination, the second one is the source. Now, how many grids and blocks should I run? In my case, for the sake of simplicity, what I'm going to do is I'm going to make the size of the grid to be the source image dot rows, and the size of the block to be source image dot columns. So basically, for each row, I'm going to create a block, and then I'm going to run the exact same number of threads that are in that row, the same number of columns that are in that row, and then I'm going to invoke my kernel. And finally, writing this kernel will become incredibly simple. You need to create an integer, and I call this index, which is going to be equal to thread index.x plus block index.x times block dim.x. And the finality of it is that we do the destination at location index to be equal to 255 minus source at the location index. And this is your kernel. So if we run this program, this should work, and we should not get any error. And my program did work. The only thing is that I'm not showing the image in the imshow. So I'm going to go ahead and imshow and call it GPU output, and this will have my GPU negated image. Okay, my GPU negated image is gray, which means that, oh yes, I need to bring all this CUDA material with the GPU image inside of the else statement. So we create the three images, we read the input image, we create an empty CPU negated and an empty GPU negated, and then we call the CPU negate function to calculate from the input image the CPU side, and then we call the negate with CUDA program function to take the input image and calculate the GPU negated, and then we show all the three images. So let's see if this works. And there you go. So as you see here, this is my original image. This is my CPU output, which looks fairly negated. And this is my GPU output. And the GPU output and the CPU output should look exactly the same. The difference is that the CPU output runs this in serial, runs for every single pixel and calculate the negation. The GPU output runs in parallel. It runs one function to work on one pixel at a time, and then it runs this function multiple times in parallel on all of the pixels in the image to get the calculation done. So this is it. I wrote a program, created a project from scratch, and added my OpenCV libraries so that I could use OpenCV functions. And in this program, I just didn't use any OpenCV functions. I just used an imshow and imread. Then I loaded an image, a grayscale image, and created two images for the output, one for the CPU code and one for the GPU code. Then what I did is I passed the original image and the CPU pointers to calculate for every pixel. So I iterated with two for loops on every pixel, and I calculated the negation of the pixels on the CPU side. Then I wrote a program to do the GPU side calculation for me, and it was fairly easy to do. All I did is I created two pointers on the device, one pointer to hold on the global memory of my GPU, of my graphics card, the data of the original image, and one pointer to hold the data that would go into my negated image. I allocated these memory units with CUDA malloc, and then I CUDA memcopied the image data of my original image into the source buffer. And then I ran my kernel, and the kernel basically for each index of the thread, I associated it with the number of that pixel. Then I calculated the negation. Once I had the negation calculated, I CUDA memcopied back from the destination buffer, the output buffer, from my graphics card RAM into my CPU RAM, which is my output image data. And then I'm showing the results. So again, input image, CPU side, and GPU side. Well, I hope this clarifies things a lot for you to be able to get on your project and work on your project. And if you have any questions, let me know. And this unit is going to take about 3 weeks worth of time. So pace yourself and try to accomplish all of the tasks needed in this unit, and this is a very important unit for us to get on, because from this point on we'll do a little bit of more programming every single unit to get some experience in CUDA. Well, I hope that you enjoy this Unit 5 of Fundamentals of CUDA Programming, and we will see you in the next unit. Thank you.